Hello everyone. In this video, I'll be discussing electrostatic discharge ESD in integrated circuits. We will explore what an ESD event is, the physics behind it, how it occurs in ICs, its adverse effects, and the techniques used to mitigate those effects. So let's get started. First, what is an electrostatic discharge event? As a simple definition, electrostatic discharge is a sudden transfer of electric charge between two objects which are at different electrical potentials when they come into contact. Let's break down how this phenomena occurs. When two materials with different tendencies to gain or lose electrons based on their triboelectric properties are rubbed together, friction causes redistribution of electrons. One material loses electrons and becomes positively charged, while the other gains electrons and becomes negatively charged. Now, if one of these charged objects touches a conductive surface, the stored electric charge rapidly flows through to balance the potential difference. This results in a high voltage spike, often reaching several kilovolts. That voltage spike can produce a high current surge, potentially damaging sensitive electronic components, or in harmless cases, just giving you a small shock. Let's talk about some daily life examples of ESD, which most of us have experienced. Suppose we put on a coat or a sweater, and then if we touch the metal door handle, we often feel a small shock or zapping sensation. This occurs because while touching the sweater, some charges transfer from the fabric to our hands. After this, when we touch the metal door handle, the stored charge in our hands flows and balances with the metal handle, creating a zapping feeling to the person. Another example is when we rub a plastic balloon to our hair, and then if we try to stick the balloon to the wall, it sticks. This is also due to electrostatic attraction. Now let's discuss how an ESD event can reach to the chip and damage the semiconductor devices. To understand this, we must know that the interface between a chip and the outer world is the IC package. IC packages provide the electrical and physical connection from the board to the chip. IC package pins or leads are the primary entry points for ESD events. During manufacturing or testing in lab, charge transfer can occur to and from IC packages due to human handling or contact with an equipment. For example, suppose a technician touches a package pin after walking on a carpet. Then a sudden transfer of charge can take place, which can lead to electrostatic discharge. Similarly, ESD can happen when charged tools or test probes contact the exposed pins of the package. The ESD events can generate extremely high voltages in order of kilovolts. This high voltage can ionize the air or break down the semiconductor junctions, creating a conductive discharge path. Once the discharge path forms, a large current in order of amperes flows within nanoseconds, generating localized heat. This can damage the package and the chip enclosed inside. To give an idea how severe ESD can be in ICs, when a user touches a package pin after walking on a carpet, the resulting charge transfer can generate a voltage exceeding 10,000 volts. This can lead to a peak current of 1 to 2 amperes lasting around 100 nanoseconds, enough to melt or burn out silicon structures within the chip. Now we know how ESD can occur in IC packages while handling. Let's understand how it propagates to the chip. IC packages contain metal pads or metal contact areas that electrically connect package pins or leads to the chip's internal I/O circuitry. These connections are typically established using wire bonding or flip chip bonding techniques. In the image here, a wire bonded connection is shown between the package pad and the I/O pad sitting at the chip's periphery. Thin wires, usually gold or copper, form the conductive link, enabling signal transmission from PCB to the package and finally to the chip. During an ESD event strike at the IC package pin, the high current surge can travel from package pad directly to the I/O circuitry. Without proper protection, this transient energy can cause gate oxide breakdown or a junction burnout. It can also further propagate in the chip's core, damaging sensitive internal transistors and logic gates. Now we understand the importance of ESD protection circuitry. But before we discuss that circuit, let's first take a closer look at the design and functions of the I/O cells which contain I/O pads. I/O cells or input-output cells are buffer circuits that interface the chip's internal digital logic with external components such as other chips or systems on the printed circuit board. These cells can be configured as input buffers, which receive signal from the external world, or output buffers, which drive signals from code to the external circuits, or at times as tri-state buffer, supporting bidirectional communication. The diagram here illustrates a bidirectional I/O buffer. The blue path shows the input buffers sending signals from I/O pad to the chip's core, and the green path shows the output driver transmitting signals from core to the I/O pad. Let's summarize some of the key functions of the I/O cells. The core typically operates at lower voltages, for example 0.5 volt, while the external signals may use higher voltages, for example 1.8 volt or 3.3 volt. I/O cells translate signals between these voltage domains. Internal logic signals are often too weak to drive off-chip loads. The I/O buffer cells include robust output drivers capable of sourcing and sinking higher currents. In the I/O cells, the input buffer path incorporates the protection circuitry to safeguard the core from ESD events. The function of the protection circuitry provided in I/O cells is primarily to divert high current away from sensitive internal components and clamping excessive voltages during an ESD event. Now let's look at the ESD protection circuitry. The ESD protection circuitry, which is designed in I/O buffer, consists of two main components, a current limiting resistor and diode clamp. Let's find out how these components help to safeguard the chip during an ESD event. The current limiting resistor is placed in series with the I/O pad and the chip. When the ESD event occurs, the sudden surge in voltage causes a potential spike. The resistor increases the overall resistance of the path, which helps to limit the amount of current flowing in the chip. This reduced current flow minimizes the risk for internal damage. Now let's talk about clamp diodes. During normal operation, these ESD protection diodes remain passive. They behave like small capacitors with very low capacitance and don't interfere with the chip's functionality. However, when an ESD event occurs, these diodes spring into action. This clamps the sudden surge to a safe level, preventing it from exceeding the chip's maximum operating voltage. Let's consider an example with two silicon diodes D1 and D2, each having a turn-on voltage of 0.7 volt, and observe how they operate during an ESD event. First, during the positive surge, if the voltage at the I/O pad suddenly rises above VDD plus 0.7 volt, the diode D1 becomes forward biased and it turns on. It conducts and passes the excess current to the VDD rail. Decoupling capacitors between VDD rail and ground absorb this surge and protect the chip's core. Effectively, the voltage at the I/O pad is clamped to VDD. On the other hand, if the voltage at the pad becomes significantly negative below zero, the diode D2 becomes forward biased. Since its anode is at ground and the cathode is at the negative voltage, it turns on and clamps the pad voltage to 0 volt, again safeguarding the internal circuitry. This diode clamping mechanism prevents the destructive voltage levels from reaching to the sensitive transistors. Some of the key benefits with these diodes are they react within nanosecond, making them ideal for transient events like ESD. Also, they consume almost no power during the normal operation. Understanding and implementing robust ESD protection is essential for ensuring the reliability, performance, and longevity of the electronic devices. This is all for this video. Thank you for watching. I hope this gives you a clear picture of why ESD matters and how we design I/O cells to protect the chip core against ESD events.